Hello, everyone. This is the lecture for section 3.1, complex numbers. So, uh, in chapter 1, we figured out how to write mathy stuff. So that encompassed functions notations, how to write functions, how to deal with them, inverse functions, right? So that's the stuff that's in general what we need for math, just to write it down, just to put it on paper, okay? In chapter 2, we dealt with lines. That's all we did, right? How to graph them, what an equation looks like, and then trying to apply it to real world stuff, right? Chapter 3 deals with polynomials. Okay, so stuff that's x squared, x cubed, x to the fourth, x to the fifth. And we're going to go through the same sort of story with it, right? We're going to learn what they are, how to work with them, the bits and pieces that are important within them, and then try to apply them to outside stuff, okay? But before we do that, okay, we have to cover complex numbers, okay? Or some of you guys might remember it from high school, uh, imaginary numbers, okay? So this is what I need to cover first before I do anything, remotely related to polynomials at all, okay? So in this section, I'm just going to define what the complex numbers are, why we have them, and how to play around with them, basically, okay? The first thing I want to do is define what a complex number is, okay? So I'm going to highlight the important stuff right now, okay? A complex number is actually this right here, this thing down here, okay? A complex number has two parts. It has a real part and it has an imaginary part, okay? And I know that's just the worst choice of word for something mathematical, just because you think that we are imagining new numbers just because we can. And it's not. It's not because of that, okay? So I want to actually explain this right here. It's that the purpose of an imaginary or the complex numbers, right, is to complete our ability to write down mathematical stuff. Okay, so there has been stuff in the last couple hundred years, okay, that up to a couple hundred years ago, we had no idea how to write down. We had absolutely no idea how to write down. So mathematicians from around the world said, we should do it this way. And that's why we have complex numbers. And I'm going to explain what I mean by that, okay? And to help us understand what I mean by uh, being able to write, being able to, formulate mathematical stuff, right? To complete our idea of mathematical stuff, right? I'm going to go through sort of like a super fast history lesson, right? Uh, with my two cavemen here, okay? Meet my two cavemen. This is Unga, and this is Bunga, okay? Okay, so here we go. Here's the explanation for why we have complex numbers. I know this is going to sound super weird because I'm talking to you about Unga and Bunga, but it makes sense. It makes sense. So just play this out, guys. Okay, guys, ready? Okay. So Unga and Bunga both have three rocks. Here's their three rocks. Okay. They're their three rocks, right? So way back in the day, probably not when cavemen are around, right? Maybe a little farther ahead, right? Unga and Bunga probably needed a way to write down three or two or one, right? Okay. That meant, right, that we had to develop something, right, to denote 1, 2, 3, 4, 5, 6, 7, 8, 0 as well, right? And that meant that we had to construct what we call the natural numbers. Whoa, numbers. Okay, now if I'm going to grab this, I'm going to move it over a little bit. Okay, if you go into math, higher up math textbooks, you see this symbol written down. Not that. Sort of like a thick N. like that. There we go. A bold-faced N, something like that, right? Okay, so just keep in mind, right? In order for us to develop the idea of 0, 1, 2, 3, 4, we had to develop something so that we had something to count, right? That's actually another word, another way to describe the natural numbers. So 0, 1, 2, 3, 4, 5. In textbooks, we call them the natural numbers, right? Other textbooks call them the counting numbers because it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, cool. Okay. Unga grabs one of his rocks and he accidentally drops it. Okay. Actually, let me not do drop it yet. Bunga steals one of his rocks. So now he has one more rock, right? But what happened over here with Anga is he got one rock taken away, right? So now we have to develop an idea, right, of taking away stuff, okay? We have to develop the idea of taking away stuff, okay? That is what we call the integers, right? And what you would see for this one is something that looks like this in textbooks, like a thick Z, a real fancy Z, okay? So Bunga took one of Unga's rocks. Here it is. That's this one right here. Cool? All right. In taking that rock, Bunga broke it in half. So now there's, come on, there's yeah, and So he broke it in half. There are two pieces, right? They're not the same size as the big rock, right? But they're half of one rock, right? So now we have to develop a way of denoting, right, that you have one piece of a whole, right? Or maybe multiple pieces of a whole, right? In this case, right, if we grab one of the halves of the rock, right, we have one out of two portions, right? So that meant we needed to find, or we needed to develop, right, a way to represent portions of a whole, right? That's where we get the rational numbers, RS. And what you see in textbooks is like a Q, but sort of like a fancy Q. It's a bold face, like an English looking Q, right? Okay. Are we good for now? Hopefully. Okay. Follow along. Okay. So Bunga broke one of his rocks in half. God dang it. So he grabbed another one. He grabbed one of the other rocks and completely slammed it until he pulverized it. He got so mad, he pulverized it, and all you have is like dust. Just a bunch of dust. So now we have, this is not part of a whole, really, right? There's way so much. There's so much just dust, right? Sort of like an infinite amount of dust, right? Does that make sense? That came out of this one rock. Okay, so now we have to figure out how we can develop how to denote this, right? And this is what we call the real numbers. And what you see in textbooks for this one is something like this. Okay, I think I might have written this in either in class, or I might have written it in another section, right? Okay. Okay, so here we go. Hopefully you guys see the progression, right? Let me cover it all again. Okay. So at the beginning, everybody had three rocks, right? Unga and Bunga had three rocks, right? We had to denote how to write the number 3, right? Or 4, or 5, or 6, 7, 8, da 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 da, right? That meant we needed to figure out how to write those numbers. That's where the natural numbers came in, right? Okay. Bunga took one of Unga's rocks. So at one point, somehow, some way, right, we needed to figure out how to denote the taking away of something, or the subtraction of something, right? Because Unga lost one of his rocks, right? So uh, we needed to develop something to denote negative, that something got taken away, right? That is the integers, okay? The integers are basically all the natural numbers, but then we also add in -1, -2, -3, negative. So it's all the negative whole numbers and all the positive whole numbers and 0, right? Okay, there we go. So that takes care of this, okay? Remember, Bunga, he stole that one rock and then he put it down, it cracked in half, right? Exactly into 2 pieces, okay? So now we had to develop some way of denoting, writing down parts of a whole, right? And the way we do that was the rational numbers, okay? So rational, basically every single fraction that we can possibly think of, positive and negative, okay? And then so now Bunga's all angry because he broke, one of his rocks in half. He grabs another one, so angry, he just throws it on there, it pulverizes, just a bunch of dust, right? We needed to denote how to basically write dust, right? Or the equivalent of dust. That is the real number. So this is where we can have decimal numbers, right? Either finite decimal numbers, so the decimal ends, or infinitely long decimal numbers, so the decimal does not end. It just keeps going and going and going. Any single possible number you can think of, right, is what we consider a real number. Okay? So now, hopefully you guys see the progression that, at least in math, right? Something happened that we had to develop something else for it that encompassed all the other stuff. So you guys hopefully see that the natural numbers are inside the integers, right? The integers are inside the rational numbers. And then the rational numbers are inside the real numbers, okay? But in every instance, something happened that we had to develop something new so that we can denote it, right? That is the exact reason why we have complex numbers. So complex numbers are the bottom, the absolute. And this one, you would see this. Bam. Okay, so the complex numbers have the real numbers inside them plus some extra. Just like each one of these other steps, right? Just like each one of these other steps, the one that comes after it contains the one before it, okay? Now, your question is like, so in each one of these steps, right? In the natural numbers, something happened that we needed to create the integers. Something in the integers meant we needed to write rational function numbers, right? Something in the rational numbers meant we needed to write something in the real numbers, right? So something happened that we needed to develop something new, right? So maybe your question now is, right, after this, so what the heck happened that led mathematicians to create complex numbers? And it turns out that back, this for sure, a couple hundred years ago, 300, maybe 400 years ago, mathematicians wrote some stuff down, right, that mathematically we had solutions for, but we didn't know how to write them down. And that is the problem. So we had something, right? We had a concept of something, but we didn't know how to write the solutions to these things down, okay? And that thing that we wrote down, it is very, very sort of, it's very minor, okay? But this is it. We had an equation like this. We had this equation. Somebody wrote this down. And they were like, okay, solve it. We can't. We don't. No, just no. How? Okay. This is the thing that we wrote down, and we're like, okay, we wrote this down. We now need to figure out how to write the solutions to this. Okay. This was the discovery of the complex numbers. solely because we wrote this down. Okay? Which brings me to a cool fact. In the last couple of weeks for this class, I've been throwing around two things that you cannot do in math. One of them is you cannot divide by 0, right? And the other one is you cannot take the even root of a negative. The one that people usually remember is you can't take the square root of a negative. Okay, this is where this is the point in the class where we get to get rid of that one. So it turns out you can take the square root of a negative. You can, okay? But this is what happens. You no longer talk about real numbers. You are now talking about complex numbers. Okay? That is the point behind complex numbers. We have to write this down. We somehow, somebody needed to write this down. Okay? This involves us taking the square root of a negative if we wanted to solve it right. Okay? This automatically means that we are no longer talking about real numbers. We have to go into the complex numbers to find our solution. Okay? So this is the explanation for our complex number system. Okay? So it turns out that there's one more circle here that goes way the heck out here. And it has all these other numbers contained. And this is the complex. ERS. And these are the ones that look like A plus BI, the thing that we have over here. Thing that we have over here. All right, cool history story, right? Cool history story. All right, so now you know the sort of why we have it, okay? What I want to do now is show you guys how to play around with it, okay? So let me start with a couple of examples, okay? First of all, let's just see how to play around with the square root of negative 25. So if we write it out, we have this. Whoops, 25, negative 25. Okay, so the way that we do this is this. We're going to separate away two things. Okay, so I'm going to have 25. Okay, and let me not put the little roof on it yet. And I'm going to do times negative 1. Got it? So I just basically separated away the negative 1. That's it. Okay, this splits into this square root of 25 times the square root of negative 1. Okay, this we know from up above, that is I, and then the square root of 25 is 5. So this is going to be 5, oh, an extra dot there, 5I, done. This is how we represent the square root of negative 25. Okay? Next one. Suppose we had this. This can happen as an answer. And you'll see it in some of our work. We're going to do the exact same thing that we did here. We don't mess with the 2 very much. So it's going to be 2 plus the square root of negative 9. I'm just rewriting for now. So just the 2 just gets to come along for the ride. So plus the square root of 9 times minus 1. This is the same thing as 2 plus the square root of 9 times the square root of negative 1. 2 plus the square root of 9 is 3. And the square root of negative 1, that is I. We're done. Boom. Okay? All right. Adding and subtracting complex numbers. It really just is like when you solve an equation. Treat the I as a variable. If it has an I, you can add, subtract them together, right? If it doesn't, if it's just numbers, you can treat those the same way as well. So for example, this one, let's say I wanted to do this. I wanted to add, or in this case, subtract these two complex numbers, right? So I can go ahead and do, I'm going to rewrite it really quick, plus 5i minus 3 minus 4i. Whoops, not minus there. 2. 2, that looks really funky. 2 plus 5i. I'm going to grab this negative that's right there, okay? I'm going to distribute it. So I'm going to do this. You guys remember this from maybe like a couple weeks ago. Minus 3 plus 4i. These two things right here, so the 2 and the minus 3, I can combine. And then the plus 5i and the plus 4i, I can combine those two. So then this will be minus 1 plus 9i. And we're done. Simple enough, right? Simple enough. Okay, multiplying complex numbers, okay? The first one is simple. It's exactly what you think it is, okay? We're going to grab that 4 and just distribute it in like this, okay? And whatever comes out, comes out. So 4 times 2, that's 8, plus 4 times 5, that's 20i. Done. We are done. Bam. Okay, it's the next one that's a little hard. The next one is a little different, okay? But we already know what to do. This one is going to require us to FOIL. So the firsts, the outers, the inners, the lasts. Okay, so I'm going to write it out just like I did way back when in our first or second week when we did foiling, okay? And then I'm going to reduce it at the end, okay? So 4 times 2, that is 8. 4 times minus 5, that's going to be minus 20i. 3i times 2, that's going to be plus 6i. And then 3i times minus 5i, that's going to be minus 15i squared. Okay, now, these two in the middle have like terms, right? They're both just with i's. This one we can't do anything with yet. We'll save that one for the end, okay? But since these two have i's, I can combine those two. So it's going to be minus 20 plus 6. So this is going to be 8 minus 14i, right? Minus 15i squared. Okay, now we're going to handle this, the I squared at the very end, okay? So remember this, right? I was defined from the very beginning to be the square root of -1, okay? If I grab this, right, and I square it, right, I'm going to get I squared is equal to the square root of -1, and I'm going to put the parentheses around it, squared, okay? This is getting us used to what happens with our cancellations, right? So if you guys remember, the way that you get rid of an addition is you subtract it. The way that you get rid of a multiplication is you divide it, right? Same thing works here with the square roots. So if you have the square root of something squared, they cancel, and it's vice versa as well. Okay, so this ends up being equal to just -1. We get this identity right here. I squared is equal to -1. So then that means I get to substitute that in for that I right there. Okay, so then 8 minus 14i, that just comes along for the ride. And then this is going to be -15 times I squared, which is -1. 8 minus 14i plus 15, 23 minus 14i. We are done. Okay? So you get to treat these just like we did with polynomials way back in the day when I asked you to FOIL, maybe first or second week of class, right? We get to treat them just like that. Exactly, just like that. Okay? Okay. Moving on. There's some quick checks. I'm going to make you multiply these out, okay? We'll try these in class. Now I really want to get into the harder thing, dividing complex numbers. So what we did up to now, right? We defined complex numbers. I covered how to add and subtract them. The example right before this one was how to multiply complex numbers. The last operation that we really need is how to divide them, okay? In order to divide them, okay, we need to pick up one thing, and that's the complex conjugate. Okay, so suppose you had this being your complex number. If this is the complex number that you're handling, some a plus bi, okay, then the complex conjugate is going to be a minus bi. All you do is you switch that sign in the middle. If it's plus, it's minus. If it's minus, turn it plus. Everything else stays the same. Okay, so leave everything else unchanged. Just leave it alone. Okay, so we have two examples here, these two. Okay, for A, the complex conjugate is just going to be 2 minus the square root of 5i. And I'm switching stuff around here. I like to have the I back here. I'm just giving you guys an example. You can switch these around. It's still multiplication right here, right? So if you remember, 5 times 3 is still the same as 3 times 5, so multiplication can switch them. I can still do that here, okay? For B, the complex conjugate, 7 plus 1/2 I. Done. Those are it. Nothing extra. Okay. We need the complex conjugate to be able to do a division. And that's what we're going to do next. Okay. So what we're trying to do here is divide these two numbers. So divide this by this. So writing it out, 2 plus 5i divided by 4 minus I. This is what we're trying to do here. Got it? Okay. In order to do the division, we have to multiply both the top and the bottom by the complex conjugate. So, and in this case, we need to multiply it by the complex conjugate of the bottom. So we need to multiply the bottom and the top, in this case, by 4 plus I. 4 plus I. Okay, I'm going to write it out. 2 plus 5i, 4 plus I, all over 4 minus I, 4 plus I. So what we're about to do, okay, just keep a track of this, we're going to do foiling on the top and on the bottom, okay? If you need to read this over, if you need to watch this over, do it, okay? So you can follow along step by step, okay? So I'm going to do the top first. First, outer, inner, last, okay? So the firsts, that's going to be 2 times 4, that's 8, plus 2i, plus 20i, plus 5i squared, divided by. Now I'm going to do the bottom. First, outer, inner, last here. So firsts, outers, inners, last. The firsts, 16, outers, plus 4i, minus 4i, minus I squared. This looks ugly, right? But it's not as bad as you think. Now we can handle this completely separate, right, on top and on the bottom. So let me redo that line that goes through the middle. There we go. Okay, on the top, the 8 just gets to come along for the right. So 8 plus 2 and 20i, that makes 22i, plus 5i squared, divided by. On the bottom, the plus 4i minus 4i, that cancels out. That's the reason why we multiply it by the complex conjugate. It turns out that will disappear. So we get left with 16 minus I squared. Okay, from the previous example, right? These two are I squares. We know what I squared is now. That's -1. So 8 plus 22i plus 5 times -1 all over 16 minus -1. Okay? That's where these i's come from. That's what the -1s come from. Okay? And then we can rewrite 8 plus 22i minus 5 all over 16 plus 1. So since it's a minus a negative, okay. Reduce stuff, 8 minus 5, that leaves us with 3 plus 22i on top over 17. So I need to write it in standard form, okay, just in case you guys get a question on this in the online homework. 3 over 17 plus 22 over 17i. Both of these answers, at least for me, are completely valid. One is in standard form, the latter one, this one. The other is in a much more manageable form that's still equivalent. Okay. Notice in this standard form, we have the real part and the imaginary part. They're both separated away. That's it. That's the only difference. Okay. Okay. After that, we've got quick checks. Okay, we'll try these out in class. But now comes this thing. Hopefully you guys saw, right, at least the first two. I squared. So we know that this is going to be equal to the square root of -1. I squared, right, we did this already, so it's the square root of -1 squared. And what happens here is those two cancel, and you get left with just -1. Okay, so I'm going to highlight the tail ends here, okay? Okay. I cubed. Okay, that is the same thing as I squared times I, right? We know what I squared is. We can't reduce it other than just make it the square root of -1, right? But the I squared we can. That's -1, right? So then this is equal to -I. Okay, that was I cubed. I to the 4th. I squared times I squared. Okay? We know what both of these are, right, from up above. -1 times -1. -1 times -1, +1. Okay, here we go. I to the 5th. Okay, hopefully you guys see this. I to the 5th is I to the 4th times I. We know what I to the 4th is. We just did it. And I just is I, right? So this is 1 times I, which is just I. Okay. I to the 6th. Let me do one more. Hopefully you guys see the pattern already. Okay. So I to the 6th is I to the 5th times I. I to the 5th, we just did it. It's I. So we have an I times I. This is I squared -1 because we did I squared. Okay, so I want everybody to see this. So this is to the power 1. This is to the power 2, 3, 4. Yeah? After that, it starts to repeat. This is the same as I, so this is the same as the power 1. You guys see that? This is the same to the power 2. So this, when we go to the 7th, this should be the same thing as we got for the power 3, and then 4. And then it should repeat again. So this should be 1, 2, 3, 4. So then that means I to the 7th, right, should be the same thing we got for I to the power 3, so negative I. I to the 8th, 1. I to the 9th, right, this should be I. I to the 10th, the same thing as power 2, so negative 1. I to the 11th, same thing as 3, so negative I. And then I to the 12th, 1. 1. Hopefully you guys see the... So if you end up doing, for these right here, if you do that, this thing, if you do this thing for all of these, you end up getting those answers. Got it? Okay. So what we get is that I to the 4th, once you get to I to the 4th, it just repeats over and over and over again. Which brings me to this. Suppose I had I to the 35th. Okay? The idea here is you want to find the remainder when you grab that power and divide it by 4. So I to the 35th, right, is the same thing as I to the 32nd times I cubed. Okay, and when you do this, right, this right here, the I to the 32nd, we know what that is because that's one of the powers of 4, right? So then that's going to be 1. And I cubed, we know that answer from our table. That's negative I. So this is negative I. So I to the 35th is equal to negative I. No need to actually go out and compute it all. You just find that remainder when you divide the exponent by 4. Okay? All right. This video was maybe longer than it was supposed to be, but it's all right. After this, it's lecture questions. If you have any questions on the stuff that I just covered, ask me during class or come to my office hours. Besides that, happy studying.